talk about F18, which is the core of the larger chip. So Ashley, are you ready?
Yeah, I'm ready. Yeah, so I'm Ashley Feniello. I was just going to present an old project of mine. It's from like 8 years ago
Mhm.
when I was first learning about the green array architecture and first getting my head around color forth and whatnot. I made this little system basically to learn, and it's probably useful to others who would like to learn as well. Um, I have this pre-recorded, so I'm just going to start the video, and then I'll be here afterward for questions. This is a presentation of an old project of mine. It's a simulator, debugger, color forth editor, and assembler. Let us play with the F18 computer. So the F18 is just one of the cores in the Green Array's 144 core chip, the GA144. Very interesting chip. I just wanted to play with programming just one of them. The documentation on their site is pretty good. It's just 2 pages, very compact, explains the entire machine. I was most interested in this little instruction set. 32 instructions, very minimal. Very Forth-like names and semantics, and I just wanted to play with it. Each core has 120 words of memory. They're 18-bit. It has 2 stacks, a data stack, and the top of that is this second and top register, and a return stack with a R register above that. Then a couple of general purpose registers, A and B, and a program counter that fetches instruction words into this I register, the instruction register, where they're executed. You can see that they're packed into slots there. So this is the project at GitHub, Ashley F. Color, and down below are some links to some blog posts going into some of the details about this wild, interesting machine and some of the inspiration for creating the project. So in 2013, I went to Strange Loop in St. Louis, and Chuck Moore showed up and talked about the Green Array chip. There's the instruction set there up on the screen behind him. And I thought it was so cool, so interesting. I bought the eval board and played with it. But I'm more of a software guy, and I really just wanted to play with the instruction set, and I wanted to write this blog series and let other people play with it also without needing hardware. So I made this thing. It's a color forth editor, an assembler, and these all work with block files and a machine that executes the assembled code. It's all written in F#, which is a nice functional .NET language. You don't need to know that language though to use the system, but here's an example of some of it. This is the definition of the machine. Just these 32 instructions, the entire machine implemented in 81 lines of code. Very simple. So once you've synced and built the project, you'll see in the bin directory separate executables for the editor, assembler, and machine. What I like to do is run tmux and just run the assembler over in one pane and run the editor in the other. And what happens is as you save things in the editor, the assembler automatically picks them up and assembles them. So you really need a special editor for color forth because the tokens aren't just syntax highlighting. They're actually colors chosen by the editor at author time, and they drive the semantics. So this is an app that has a bouncing ball on the screen. So that we have its position and direction and color, and it can move and bounce off the edges and be drawn. So red words are the definitions, white words are comments, and they can be toggled on and off like this. Green words are for literals or calls to previously defined words. And gray words are F18 instructions. So that's something special about this editor for the F18. Yellow words are macros that get expanded at assembly time. Then there's also blue words that are for formatting. So this is really just a flat sequence of tokens, but the formatting words give carriage returns and tabs and things to make it look nice. When a block file is saved, the assembler automatically picks that up and assembles it. So you can see that on the right-hand side. Here's some of the correspondences. So we have the draw word and the source on the left, and we can see that it gets assembled over here on the right to this location in memory. And you can see that the literal value there ends up becoming a fetch p, and the literal value itself is in the whole next instruction word. So that's how this works. You inline literals in with the instructions, and fetch p just fetches the program counter and increments over it. Then this call to color plus becomes a call instruction followed by the address of color plus. And the next 2 white words, or and store B, are F18 instructions directly, and they just go directly into slots. And the call to ball Y, again, just becomes a call instruction, and the remaining slot has the address. Then you can see yellow words like for and next end up getting expanded. So it does a fetch p of the value to put on the return stack, followed by a push, It puts it on the return stack. That becomes the induction counter for the loop. And there's the 2-star, the body of the loop, and then the next expands to a micronext, which is an interesting instruction that just creates a little tiny loop inside of that single instruction word. So the assembler writes to block 0, and the machine conveniently boots up with the P register reading from block 0. So just running it, we can see what happens. We get this ball bouncing around the console, leaving a colored trail. Nifty little demo. Alright, so let's go take a little closer look at the editor. So it's a very Vim-like editor. Block 1 has instructions. HGLK will move around. You can jump between definitions. You can set the colors of the tokens with Shift R, Y, G, W, and A. This is why we really needed a special editor to be able to edit color forth this way. Since W comments things out, it also advances the cursor and it makes it easy to just comment out whole lines like this. You can toggle the format words, the blue words. You might need to be able to see them so that you can edit them. And then you can also toggle comments. So this is kind of like the shadow blocks idea in Array Forth, keeping comments and codes separate. At least this way you can toggle them on and off. So I like this. Focus on just the code. And it's a block editor, so you can just press the number of the block you want to load. You can save with S. You can cut and yank with X and Y. And it just keeps a stack of what's been cut. You can go around in PPP to paste back from the stack. So even though it's just one token at a time, it's very easy to move things around this way. Then just like a normal Vim, you have normal mode for just navigating, or you can go into insert mode and enter new tokens. And while entering code, automatically the first word is red and then it switches to green unless you choose otherwise, and you can do this while in insert mode. Then also there is an infinite undo, so everything you've ever done you can just undo, and you can redo if you like. So you can be pretty fearless about editing blocks. Then you can also find the word that's under the cursor anytime and navigate around pretty easily that way. Gray word's a little bit special in the editor. It restricts you to entering only legitimate instruction names, and these get saved instead of as source in the block file. They get saved as the actual instructions. This is an idea taken from Jeff Foxworthy's AHA, and also from Chuck Moore's Etherforth did this. So it'll restrict you from converting illegitimate words to gray, and it will, beep at you if you're trying to type something while in gray mode that isn't legitimate. So that's kind of an interesting feature of the editor. So let's make a little program from scratch. So we'll make something that just prints the alphabet to the console. We'll make an alphabet word, and now ASCII A -1 in hex is 60, and 26 letters in the alphabet minus 1 again in hex is 19. So we'll iterate through those, and for each one we'll just add 1 to the ASCII value, duplicate that to keep it, and do a store B, which B initially points to the console in this machine. So that should be about it. Basically this will print the alphabet. And if we save that, we can see what it assembles to. So it assembles into these 7 instruction words. So alphabet is defined as starting at address 0, and these literals get inlined into separate slots, 16, 19, and the first instruction word has 2 fetch P's that fetch them. So what really happens is the program counter is pointing here, loads this into the instruction register, and begins executing those slots, which continue to increment the program counter past those literals. The for macro expands to just push that 19 onto the return stack to become the induction variable, and then execution continues. So program counter would be pointing here now and do another fetch P to get that 1, and then the rest of these are pure instructions, add, dupe, and store B. And then next becomes an actual call to address 3. So this is a large loop rather than a micro next loop happening within one instruction cell, which we'll see later. This is a regular loop. So it appears that this program is already in memory. It's been given addresses by the assembler, but what actually happens is this gets written to block 0, and the machine boots with the P register reading from block 0, just streaming code in one instruction word at a time and executing them. If we want it to actually end up in memory, we have to use this load macro, which inserts this little program that loads the rest of the stream into memory in the F18. So it creates this fetch P that fetches this 6, which was computed to include all of the instruction words to follow. There's 7 of them minus 1, so it's 6 for the induction loop. And then this instruction word, which is part of the stream, is just a little micronext loop. So it does a fetch P and a store increment, which stores through A, which begins life pointing at memory. So this little tiny loop will just fetch through the P register off of block 0, storing into memory. Do that 6 times, 7 times, and the program will be loaded. And then it follows with a call to the alphabet word to kick things off. So this load and init work together to wrap your program in this little loader that will stream it into the processor's memory and then start executing it. So now if we just go run the machine, we should be able to see it do what it's supposed to. It should print the alphabet to the console. And sure enough, it's exactly what it does. Now just to get a better idea of how the little loader works, I'm going to go back up here and insert a break instruction. So I actually have added a few instructions to the machine that aren't F18 instructions. This break will enter a debugger. So with this, we'll be able to see the state of the machine and step through code. So here's the entire state of the machine. Here's all the registers, the data stack, and the return stack, and part of memory is shown to the left. So what happens to start with is it fetches through the P register from block 0 an instruction word and begins to execute it. Here it itself does a fetch P that fetches the next instruction word, still just streaming in from block 0 though, not from memory. Puts that on the data stack and then pushes that to the return stack. Then this instruction word gets fetched, and this is interesting. So this all goes into the I register and begins to be executed, and it itself is a little micronext loop that just continues to be executed without anything in memory on the machine. Each step through the loop is going to fetch through P, one of the instruction words being streamed in, and then store through A and increment A. A begins life pointing at memory, so that ends up basically filling up memory with whatever's streaming in. It goes through that micronext loop 7 times, until the R register decrements down to 0. And so we have the entire program loaded. And then at that point, the final instruction word there is a call to address 0 to kick things off. So you can see everything being loaded here. And then finally, we fall out of the loop and we end up doing a call to the alphabet word and executing all of the code within the alphabet, a little program that we've already walked through. It ends up printing to the console. Of course, that's getting eaten up by the debugger taking over the console here. So I really just wanted to play with the F18 instruction set and see what can be done with this ridiculously minimal set of instructions and see what kind of tricks can be played. So for example, you can duplicate the top of the stack and XOR those together to generate a 0 rather than loading a literal, save some space. There's this not instruction. The minus sign is actually a not, a one's complement not. You can generate a 2's complement negation just by adding 1 to that. There's no subtraction instruction. There's add, but there's no subtract. But using the not and add, you can generate subtraction, either by doing that and adding 1, or you can subtract the second from the top on the stack. That's kind of reversed in just 3 instructions. Or you can push and pop from the return stack and do it in 5 instructions, but in the right order. Funny enough, there's no swap instruction. There's over, which is similar but leaves garbage behind. You can either do that and then later drop it, or because it's a circular stack, maybe just leave that forever. Or you can accomplish a proper swap in 7 instructions this way, or with a little trick, XORing twice, you can do it still in 7 instructions but using less of the stack. Or if you're willing to stomp on register A, you can save a few nanoseconds and a couple of instructions and do it this way. So there's all these nifty little tricks you can play, and it's fun to see what's possible and try your best to optimize for speed and size. So here's a pretty nifty trick for creating variables. So first of all, of course, to create a constant, just simply define a name for a literal. But then to set that constant, we do something like this. And if we assemble it, we can see what the code actually looks like. So the constant is just a fetch p return followed by the literal. So that's pretty obvious. But to store into that variable, we do something like this. We do fetch p drop store p return. So the first fetch p will fetch the instruction word here, but then drop that. And now the P register is pointing at the value, and so the store P stores into it. So it's kind of a cool little trick to just in 3 words create a variable. And we did that actually in the ball example for all the ball position and direction and color and everything were variables defined this way. Another tricky little thing to point out is that red words just define names for addresses. And there's nothing that says that a definition has to end with a return. So for example, max can be defined this way. It's just less if swap drop. And then absolute value is basically dupe, neg, and then take the max. And you can define it in this order and just allow the abs word to fall through to the definition of max. There's also nothing that says that you can't have multiple returns in a definition. So sometimes you might have an if with an early return. So there's all these cool little tricks. It's pretty fun to play with. So have fun. So there you go. It's kind of fun to play with.
Fantastic.
Thanks.
Yeah, thank you very much.